let's move on to our next unit. So what we'll be talking about this week is granular media filtration. And I use granular media as the adjective because we will talk later about membrane filtration. So I want to distinguish between what we refer to as granular media versus membrane filtration. We'll look at a brief overview. We'll look at media characteristics. We'll look at some theory. Much of what we will be actually focused on the hydraulics of both filtration and what we refer to as backwashing. So when we talk about granular media filtration, the focus really is on removing suspended solids. So granular media filtration most often follows some sort of coagulation, sedimentation, unless it's a very, very pure, clear water, in which case you can use direct filtration. But the goal is removing suspended solids. We want to produce high quality drinking water, and we want to remove bacteria. So typically, in drinking water, these are the goals: removing suspended solids, producing high quality drinking water, and removing bacteria that hadn't been removed in the previous processes. If we're looking at wastewater, so this is drinking water, we're looking at much of the same, predominantly removing suspended solids. And we may also be looking at removing phosphorus that is attached to particulate matter. So those are the predominant goals. We'll talk about depth or gravity filtration, pressure filtration, and then slow sand filtration. On Tuesday, when Paul spoke with us, he talked about the unit NTU. So N being, anybody remember what N stands for? It's nephelometric. And as Paul mentioned, it's actually Greek for the word cloudy. Nephelometric turbidity units is a standardized unit of measuring turbidity, or the clarity of water. And what you see here is that we have, I've given you two comparisons. In the US, the drinking water regulations require that the turbidity from the filters be less than 0.3 in 95% of the samples. Contrary, in New Zealand, their turbidity has to be less than 1 NTUs. Again, it's also for 95%. And then they also have an additional standard in New Zealand, which requires that the turbidity not exceed 2 NTUs for the duration of any 3-minute period. So there's both a standard for that 95% and then an upper limit. In the US, there is no upper limit. When we're looking at removal of turbidity using granular media filtration, we're focused in this region here. So we're focused on removing material that is up to about 1 micron. To give you an idea, cryptosporidium oocysts are about 3 microns in size, so we can remove in a well-operating filter. We can remove cryptosporidium oocysts. So you can see we're looking at the suspended solids. You can see bacteria in this range here. We typically will not get virus removal in a granular media filtration. Viruses are down in this range here. We have to look at other processes if we're looking at virus removal. So with pressure filtration, typically these are used for smaller systems and high purity water. So you're looking for waters that have less than NTUs in the raw water. And you're looking typically at plants less than about 50 mgd, which is actually still a fairly big size plant. Where I've seen these used most is actually on smaller plants. Williamston has a pressure filter system. Mason and Leslie both have pressure filter systems, and the system that MSU put in is essentially a pressure filter system. So instead of relying on gravity to force the water through the filter, you're actually using pressure. You can also use vacuum, but pressure is most common. With most of this, you're using some sort of a granular media, so something like sand. These have a much smaller footprint than a gravity filter, and you can operate these often with no chemical addition. Slow sand filters operate under gravity, but with a much lower flow rate. And the difference here is that with slow sand filter, what you form is this layer here of organic matter and microorganisms. It's referred to by its German name, Schmutzdecke, which literally means dirty layer. And so this is a fairly thin layer of, as I mentioned, biologically active materials, so it includes microorganisms, organic matter. And what happens is in this region here, you get degradation of organic matter. You actually get biological activity. And you get capture of your microorganisms. These are very, very common in Europe. They're used also in much now of the developing world because they don't require pumping, etc. And it's just you're allowing water to flow by gravity through this biological layer, then through sand, and then through a gravel support. Much of the removal is actually by sieving. And what will periodically be done is if this layer here gets too thick, then you drain the system, scrape off a bit of that Schmutzdecke in order to reduce the thickness of that layer, and then refill the unit and operate it again. Gravity filters, also referred to as rapid filters or depth filters, have what is shown here as a layer of our media. And we'll talk more about that, but just think of this as sand for now. It has a gravel support, so this is a support layer. It has a series of perforated laterals. The water is then collected in these. So this is perforated here. So the water can flow during operation. The water is going to flow down through this sand into the perforated laterals and then will be collected. During backwashing, the opposite happens. So now we're going to pump water back upwards. We'll fluidize this bed. So now the water layer will be up over these laterals here. So the water flows into the lateral. So this is during backwashing. This is during operation. So when we're filtering water, it's going to flow down through the sand or other media by gravity down through the support, collected in the laterals, and then we'll move on to any further treatment. Backwashing, it happens in the opposite direction. This is just another cutout. This shows what's referred to as a gullet. There is another cell here. So these are operated with two cells. So good question. Why do they backwash? Okay. They backwash for two reasons. One, let's look back here. Okay. If water flows through and that water has turbidity in it, what happens to the head loss over time? So the head loss as a function of time. What will happen as we're operating the system, we have particulates that are removed. So what do you think happens to the head loss as a function of time? It increases, exactly. Okay. At some point, the head loss will become too large in order to allow water to flow through the filter by gravity. So at that point, we would have to backwash. The other problem is that I mentioned we've got a turbidity limit. As particles collect in the filter, what do you think happens to turbidity? So we're looking at the effluent turbidity as a function of time. Less gets removed, so the turbidity increases. So there's two things that trigger backwashing. Either the head loss exceeds some critical limit, or the turbidity exceeds some critical limit. In many cases, based on experience, backwashing will actually be done on a timed cycle, just based on knowledge that, for instance, every 8 hours it will need to be backwashed, rather than watching and then backwashing manually. So this is a cutoff, as I mentioned. Your filters are always designed with two cells. So there's here, there's a whole another system mirror imaged on this side here. And that's because of the pumping and piping requirements. So you can see this gullet in the center. You have your wash troughs here. And this is an air scour system. So often what will happen is on the top of here, you have what we refer to as mud balls. These occur predominantly in the surface water system, but basically the clay particles aggregate together and they form kind of a clump. And it's really hard to remove those clumps by backwashing. So we often use air scouring to try and dislodge that material. And you'll see that in a video in just a bit. So we have these wash troughs. We have, you can see the surface wash unit here. We have the filter media here, a graded gravel support, under drain blocks, and then we have the laterals within that system. To this video. It's about 5 minutes long. I'm going to play the whole thing. It was actually produced by a colleague down at North Carolina State. And I think it's a really good way to view the operation of the filter.
We have the gullet down the middle. And yeah, we can see the drawdown happening. The water is slowly.
Okay, so what's happening right now is the video starts with backwashing. So the system, the filter's been operational, but either the head loss limit was exceeded or turbidity limits were exceeded. And at that point, then this triggers backwashing, and the backwashing process actually starts. So the reason for this is, as I mentioned, this is clearly a surface water system. So they're using that air scour to try and dislodge material that really has clogged, that's attached, that just simply backwashing the filter wouldn't remove. You can also see in this video here, back in this region here where I'm pointing to, that's the second cell. So here's your gullet down the center, and you have one cell and another cell here. Together, they make up a filter bed. Okay, so now what they've done is they've started to pump water. And notice here you can see here. So what's happened is they've fluidized that bed to dislodge particles. You want the media to remain below the top of the gullets, but you can see how violent this mixing is. And water is now flowing over the top of these troughs. And that's this dirty water, okay, that contains all of the removed particulates. that that helped. Normally we would see that typically when we visit the dye plant. If possible, they actually hold off backwashing the filter so that we can watch that in operation. Any questions about the operation of the filter? I'll post that link online Kappa as an external link, just so that if you want to watch the whole thing again, it really does help to get a sense of how these systems operate. What you see here is a plot of a filter run. So this is a plot of the effluent turbidity and the head loss. And you can see this would be the head loss of the clean filter bed. And then over time, as you operate the system, the head loss filters, and then there would be some cutoff. So this would be our critical head loss. And that's when the run would be terminated and the system backwashed. This is a plot of turbidity. Now, what you note right here is that the turbidity actually initially increases. And the reason the turbidity increases is what we refer to as filter ripening. So if this is these are our sand particles. And so here are our particulates that we're trying to remove. The particulates, this one comes here. And in order to remove particulates, we need two things to happen. We need a collision. So we need collision of the particulates with the media. And we need attachment. So that particulate has to collide with the media or the collector, and then it has to stick to it. And if it doesn't, it's going to end up in our effluent. What happens is that as one particle collects, we have multiple particles. It's more likely that the next particle will attach to it, the removed particle, than it will the media itself. So you actually get, in this initial period of time, you get an improved removal. Because of that, and because you need to essentially rinse the filter at the start, there's a certain amount of water that is actually wasted. So that water won't get distributed out to the community because the particulate levels are too high. So that becomes wasted. And then we'd really start maybe here. This is when we would start collecting that water for distribution. And that really depends on the plant. It depends on how well the filters are operating, what length of time you need to waste that initial amount of water that's treated. Just to compare slow sand filters with rapid, typically we will treat about 3 to 8 meters cubed per meter squared per day. So that meter squared is the surface area of the filters. On the other hand, your velocity through your filters is roughly up 100 times greater in a rapid sand filter, which means in terms of surface area, which one requires the greater surface area? So slow sand filters require much greater surface area than a rapid sand filter. When we're looking at the filtration, much of it occurs in the top 75 millimeters of a slow sand filter. On the other hand, in a rapid sand filter, you want to use much of that depth of the filter. So you're going to use a lot more of the media for removal. And for slow sand filtration, typically we have single media sand, and for rapid, we can have single media sand. We can have dual media, which is sand, typically sand and anthracite. And we can have multimedia, which typically is sand, anthracite, and garnet. And we use these different media because they have different specific gravities, they have different size and porosities, so we can use them to remove different particles. The anthracite we can also use, we can have a top media, above the sand of activated carbon, where we're not looking at filtration, but we're really looking at an adsorption of soluble material. And we'll talk about that when we talk about absorption. When we're looking at removing particulates, there's 5 different mechanisms that we can discuss and consider. One is mechanical screening, and this is what essentially happens in your slow sand filter. You have your particulates and your media, and the particulate is too big to fit through the pore space. And you can see this would happen on a slow sand filter, and then you would get this Schmutzdecke forming on the top of your media. Same thing happens when we talk about these mud balls. So if you get enough of these together here, then you form this kind of clump of material that is difficult to remove. We also talk about sedimentation. Here, the mass of the particle and the diameter of the particles are large enough that the particle actually settles. So this is moving by settling, and it settles, deposits on a particle. So you can see it's smaller than the pore space, but it deposits on that particle and it's removed by settling. Then we also have what we refer to as flocculation. So here, what happens, look, we've got this particle and this particle. These streamlines of the particles cause these 2 particles to collide with one another. They're able to attract, they're able to flocculate. And then that larger particle could be removed by sedimentation, or it could be removed by interception. So interception means, here's my particle. What happens here is the particle's moving down, my streamline, the water has to bend around the particle, and it just comes in close enough contact with my particle that it's able to attach. Impaction, my particle deviates from the flow path. So here, the particle is deviating from the flow path. Interception, it's flowing with the flow path. That's really the big difference between those two. In all cases, you need a collision to occur, and you need attachment. So in order to get removal, we need both of those happening. Now, we can also get detachment. In order for the removal to be significant, attachment has to be greater than detachment. This table gives you a sense of the physical properties of the filter media, and it's broken down by the different types of material. So we have anthracite coal, we have GAC, which is granular activated carbon. As I mentioned, this is a sorption process. It's used for sorption, not for physical removal by filtration. Garnet, ilmenite, and sand. Now, it's a number of parameters we use. One is the effective size. The effective size is defined as the sieve size for which 10% of the sand passes. So think back at the video we watched with particle size distributions and sieve analysis. So it's the diameter or the mesh size for which 10%, and it's a cumulative, 10% of the sand passes. This controls head load. The uniformity coefficient, refer to it as UC, is equal to D60 divided by D10. So D60, it's the sieve size for which 60%, and it's a cumulative, 60% of those particles are removed, divided by T10 is our uniformity coefficient. This table from the textbook provides you with a number of values. On the other hand, the GLUM standards are slightly different. So I'm going to cross this out and I'm going to give you the GLUM standards. Quite a narrow range for the effective size. This is in millimeters. For the uniformity coefficient, according to the GLUM standards, this should be less than or equal to 1.65. Hardness, this is the Mo hardness. It is not the hardness that we talked about. It is not sum of polyvalent cations. So what's the Mo hardness? Which is easier to make a scrape into? Limestone or diamond? It's essentially the resistance to limestone, okay? So Mo hardness is a resistance to fracturing. It's how easy it is to put a scrape into that material. The lower the hardness, the more likely during backwashing your media breaks apart, and you don't want the media breaking apart during backwashing. The specific gravity is obvious what it is. The specific gravity, for instance, for anthracite coal is greater than 1.4 for the GLUM standards. And then sphericity is essentially how spherical it is. So sand 0.7 to 80%, compared to a sphere, it's roughly 75%. Essentially. One mention I want to with the GLUM standards. I posted the 2012 GLUM standards last night. It's in the design project folder on LonCappa. I was hoping to post the 2018. I had to purchase that. It's about $13. And when I got it, it said that I'm not allowed to distribute it. My plan was to originally put it on Kappa, but I didn't for that reason. The GLUM standards are perfectly, 2012 GLUM standards are fine. As I go through it, if I see any differences, I'll let you know. But you can just design based on the 2012 GLUM standards. Last thing that I haven't mentioned is porosity. And the porosity is the volume of the voids divided by the total volume. So that's the porosity. There are a number of equations that are used to relate head loss to the various different parameters that we measure. This is just one of them. Number of things I'll mention. I'm not going to go into this in any great detail, but I want to mention a few things. One, as the approach velocity, also referred to as a filtration rate, face velocity, loading rate, as this increases, your head loss increases. And notice, because the approach velocity term is squared, small changes in the approach velocity greatly impact your head loss. As we increase the depth, we also increase head loss. As we increase the grain size of the media, the head loss decreases. So the bigger the media, the lower the head loss. As we increase porosity, we decrease head loss. So, and small change, because this is to the fourth power, small changes in head loss, small changes in the porosity will have a large impact on head loss. I'm going to stop there.